Welcome back. In this video, I'm going to solve exercises 15 to 17 of chapter 1, mainly about limit points and boundaries. Exercise 15, let A be a subset of a metric space and let X be a limit point of A. So what does this mean? It means that, by definition, every neighborhood of X meets A at a point different from X. So when we remove X from the intersection, we get a non-empty set, but actually more is true. It's not only empty, it's infinite. Okay, so this is what we have to show. Okay, so we reason by contradiction. Suppose that there is a neighborhood of X. We can take it open, as we know. So suppose that there exists an open neighborhood U of X that intersects A at finitely many points. So when I remove from the intersection X, we also get a finitely many points. Okay, if the number was M, then when you remove X, we get M minus 1. Okay, so suppose that therefore U intersects A without X at finitely many points, X1, etc., Xn. Okay, but we already observed that we know that in metric spaces, singletons are closed, and therefore finite sets are closed. So the set X1, Xn is closed. And we know that when we remove a closed set from an open set, we get an open set. So V is an open set. And X is in V. X is in U, but X is different from X1, Xn. So X is in V. So V is a neighborhood of X. But by construction, V does not meet A without X. So because I removed everything. So therefore, A minus, so this I get a contradiction. Okay. Therefore, a finite set has no limit points. Okay, because if it had a limit point, then every neighborhood should intersect A at infinitely many points. So the set A in particular should contain infinitely many points. Okay, the next exercise. If A is a subset of a metric space X, we have to prove that if A is closed, or A is closed if and only if it contains its boundary, and A is open if and only if it does not meet its boundary. So this corresponds to our intuitive understanding of the boundary. Okay, so, and this may help justify the notions of open set and closed set. Okay, so why it's open? Because it does not meet its boundary, or it does not contain the boundary. Whereas the closed set contains the boundary. Okay, but we couldn't have taken this as a definition because we didn't know what does boundary mean. Okay, now we know the boundary of a set is the closure without the interior. Okay, so first question, two implications. Suppose first that A is closed. Then we know that it's equal to its closure. But the closure of the boundary of a set is by definition a part of the closure. Okay, by definition. Therefore, so if A bar equal to A, then the boundary of A is in A. The converse, if the boundary of A is contained in A, I have to show that A is closed. So how do I prove this? There are several ways. The best thing here in this case is to show that A is equal to its closure, or it contains its closure, because we always have A is in A bar. So we pick an arbitrary point X in A bar, and we have to show that it's in A actually. Now we have two options. If X is in A bar, then either X is in the interior of A or it's not. Okay. If it's in the interior, there's nothing to prove because the interior is contained in A, so X is in A. So, and if X does not belong to the interior, then by definition, X belongs to the boundary because it belongs to A bar and not to the interior. And the boundary is contained in A, so X is in A. So in both cases, X is in A. Therefore, A bar is contained in A, and therefore A equal A bar, and therefore A is closed. Second question, also two implications. If A is open, then A does not meet its boundary. And this is almost trivial because the boundary is a bar without a circle. But if A is open, then A equal to a circle, and therefore the boundary of A is a bar without A. And so the boundary is in the complement of A, so it does not meet A. Conversely, if the boundary of A does not meet A, we have to prove that A is open. How do I prove that? One way is to prove that A is equal to the interior. How do I prove that A is equal to the interior? Double inclusion. Of course, the interior is in A, so we have just to prove that the converse, the reverse inclusion. So we pick an arbitrary point X in A, and we prove that's in a circle. Okay, since A does not meet the boundary of A, then X is not in the boundary. But the boundary is the closure without intersected with the complement of the interior. So what does it mean that X does not belong to the intersection? It means that it does not belong to either one of them. So either it is not in A bar or it's not in the complement of a circle. But X is in A, so it's in A bar. Therefore, the only possibility is that X is not in the set. What does it mean that X is not in the complement of a set? It means that it is in the set. So X is in the interior of A. So any point in A is in a circle, and therefore A is contained in a circle, and therefore we have equality, and so A is open. Okay. Last exercise, we have also a subset A of a metric space, and you have to show that if A is open or closed, then the boundary has an empty interior. It's not always true, because if you take A to be the rational numbers, then the boundary is R, and R, the interior of R is R. So it's not true. But Q is not open. The rational numbers are not open. Okay. This also corresponds to something intuitive. If you have an open set, its boundary cannot contain a ball. Okay. This is the meaning of empty interior. And same thing if it's closed. So we'll deal first with the case of A open. And we reason by contradiction. If the boundary has a non-empty interior, then it contains an open set. And the boundary in this case is just a bar without A, because A equal a circle, because A is open. So we have now a non-empty open set O contains an A bar without A. Okay, so O is contained in the complement of A, so O doesn't meet A, right? Because O is contained in this set. Okay, now therefore if X is in O, then X is not in A. Therefore, okay, so if X is in O, then and O is contained in the boundary, then X is in the boundary. And the boundary, as we know, is contained in A bar. And now we have a contradiction. Because X is in A bar, so according to proposition 1.8, every neighborhood of X should meet A. So, but here we have an open set, a neighborhood O of X, does not meet A, so we get a contradiction. So this contradicts proposition 1.8. Okay, this rules the case where A is open. Now, the case where A is closed can be deduced from this one, as I will show you now. If A is closed, then the complement of A is open by definition. And according to what we said, the boundary of X without A should be empty. Now, what is the relation between the boundary of A and the boundary of the complement of A? Intuitively, the boundary of A and its complement should have the same boundary. We expect that. And this is indeed the case. Because, so we go back to the definition. The boundary of A is A bar without the interior. So it's A bar intersected with the complement of the interior. But by exercise 7 or 9, I think, this is the complement of the interior is the closure of the complement. So we can write the boundary as the intersection between the closure of A and the closure of its complement. Okay, and this is we should understand that. So because the boundary is something in between A and its complement. And therefore, the boundary of the complement is the same thing. It's x without A, but the complement, it's the closure of x without A intersected with the complement of the complement. So by symmetry. So this formula is symmetric, unlike this. Okay. So this formula, this is another characterization. I didn't mention it in the lectures, but this is something that you can easily deduce. Okay. So always in any metric space, A and its complement have the same boundary. And therefore, if the boundary of the complement is empty, then the boundary of A is empty, and that's it. So this concludes exercise 17 and this video. Thank you for your attention, and see you next time.